operations that are specified in that interface are implemented. In this segment of videos, we'll consider stacks. A stack is a specialized list where items may only be inserted and removed from the top of the stack. We see many examples in everyday life, such as with a stack of books, or a Pez dispenser, or even our email inboxes. Stacks are called last in, first out protocol, or LIFO. This is because the newest element is on the top of the stack, and the oldest is at the bottom of the stack. Let's consider stack operations now. We should be able to push an item onto the top of the stack. We should be able to pop or remove an item from the top of the stack. We should be able to see the item on the top of the stack, so that's top, and you'll notice that top should not alter the stack. It should just permit us to view the top of the stack. We should be able to check the size or the number of elements in the stack, and also whether a stack is empty or not. In order to implement a stack, we have to have an underlying list in order to contain all of the items in the stack, and we need a pointer or an index to the top of the stack. Let's consider some stack axioms now. So this is how a stack should behave as a result of each of the operations of the ADT. So for example, if we have a stack S and we push an item on and then call top, we should have the item we just pushed at the top of the stack. Similarly, if we have a stack and we push an item on and then pop, then the stack should be the same as though it was before we pushed the item on. Let's consider what a stack will look like for the following operations. So we start off with an empty stack, and we push the integer 5 on the stack, and then we push the integer 4 on the stack. Now, when we call pop, we will remove 4 from the top of the stack. And when we do that, our stack will only have the element 5. Then, when we call top, we will return the element 5. But you'll notice that our stack is not altered. 5 is still at the top of the stack. We just returned it as a call to top. Now let's consider how we may implement a stack class. So here we have a stack in class. Its public functions include a constructor, a destructor, size, and empty functions, as well as functions to push a value onto the stack, to pop a value from the stack, and also to check the value at the top of the stack. Now, some decision that we need to make is how will we actually store the items in the stack. We could use a linked list, or we could use a dynamically sized array. If we use a list, we could use the STL list class. So we can have a list of integers for our items, or if we want to use a dynamically sized array, we can use the STL vector class for our list of items, and that would be a vector of ints. Now, the other thing we need to consider is we want to keep track of the top of the stack. So we can do this by keeping the index of the top of the stack. And what's important to consider is what do we want to have it, the index be for the first element or the last element. So for example, if we use the STL list, we may want to have our index be the beginning of the list. And the reason for that is we just may want to remove and insert at the head of the list. In contrast, if we use the STL vector, we may want to have our index be the size -1. and this is assuming zero-based indexing. And the reason for that is that with a vector, it is more efficient to add and remove from the back of the vector rather than from the front, because it avoids having to do any copies. So these are some things you want to consider when we would be implementing a list. And in this example in particular, we're only using composition. This is just an example of how we might use composition. Now, stack conditions that we have to be concerned with is underflow, which is when we want to pop from an empty stack, and also overflow, which is when we want to push onto a full stack. And that's really only a concern when you have an implementation that would have a list that has a limited capacity. Okay, now let's